Good morning, everyone. Welcome to the third day of the Second Chennai Symposium on Gravitation and Cosmology. We have an exciting sessions in the morning, and the chair for the first session is Prayush Kumar Hazra from the Institute of Mathematical Sciences, Chennai. I will request Dheeraj to take over. Dheeraj.
Thanks, Sriram. Good morning, everyone. We have two talks in the morning session. The first one is by Professor Prayush Kumar from ICTS, and the second one is by Professor Tirthankar Roy Chaudhary. Professor Prayush Kumar is going to talk about numerical relativity for the gravitational wave astronomy, the past, present, and future. So you can post your questions in the chat box. So if I find something within 20 or 25 minutes, I'm going to request the speaker to address them. And after that, I will reserve the questions for the question answer session, which is in the 40 plus 5 minutes. Okay. So I'll hand it over to Professor Prayush Kumar.
Thank you very much. Good morning, everyone, and thank you all for being here. So let's get started. So today I want to talk about numerical relativity, give a brief summary of the field, what has happened, where we are so far, and where we are going in the coming future as our detectors of gravitational wave signals become more and more sensitive. So any story must start with the first and most basic question: why numerical relativity at all? Right? So, and the answer, of course, comes from the fact that we are observing gravitational waves quite plenty these days. So we find that most of the stars in the universe exist in two-body systems. And many of these two-body systems actually survive as these stars evolve and go through their lives to form individual black holes and their big binary black hole systems, which then go orbit around each other, emitting gravitational waves. And finally, they merge to form a highly distorted dynamical black hole, which settles down into a Kerr solution after radiating away its asymmetries. So it's really in understanding the last few orbits of this process, especially and the merger process, that we really need to understand this process through the lens of all the nonlinearities that general relativity brings with it. And therein lies the need to do numerical relativity without any approximations. Of course, this is only half the story. The other half is that the bulk of the binary black hole population that LIGO and Virgo are seeing these days comprises of very heavy binary black hole mergers. Right? So by very heavy, I mean binaries that are 40 solar masses, 50 solar masses or more. And the reason that comes into picture here is because heavier signals, heavier binary signals are actually short. As much as they're visible within the LIGO-Virgo band, they only comprise of the last few orbits of the entire process. And the merger portion is especially rather pronounced in these heavy binary black hole signals as compared to the lighter versions of the same binary mergers, right? So you can see the same thing in frequency domain here, where the heavier, less heavier, and the least massive binary signal is plotted here in frequency domain against the noise spectrum of the LIGO-Virgo detectors. And you can see the very first event actually merged at a couple of 100 hertz only, which makes most of its signal content be in these last few orbits. And it's only with numerical relativity that we can actually understand what is going on in this strongly dynamical region of gravity. So how does the entire field of numerical relativity helping the being applied to gravitational wave astronomy these days? Well, we have our instruments from which we are continuously collecting strain data, which is then processed through a series of stages before any detection of gravitational wave is declared in that data. And all of these stages, there will be the first match filtering stage, or second, once you have a candidate, a signal consistency test stage, both of these stages are informed by approximate models of what we expect the signals to look like. Right? And these models are what generate the waveform templates that are used here. Once you detect a signal, then you must try to understand it. What was the source of this signal? Where was it located? and so on. And all of that information again comes using waveforms as templates into and applying a framework of Bayesian parameter estimation to the data. Right. So the central to the analysis of these compact binary merger gravitational waves are waveforms, and numerical relativity both directly informs these templates. Also, it indirectly informs these templates by informing the construction of waveform models that in turn are used to generate these waveform templates. So that is sort of the pivotal role of numerical relativity at this juncture. And in fact, it is not, if we look more carefully, we find that NR is actually necessary for doing binary black hole science with the LIGO-Virgo detectors. For example, without information from NR, most of the first events would have been detected with much lower confidence than they were. They would be more like probable events rather than confident detections. And if GW150914 source had emerged not a little further away than it did, it would have not been detected in Livingston at all. And even if we were to see many of some of these, some of the sources that we have seen so far, we would only approximately measure the characteristics of the source that emitted these signals. So for example, here, this figure shows the measurement of the mass and the spin of the final black hole that forms after merger, as measured using only the in-spiral part and the in-spiral plus merger ring down part. And you can immediately see that your measurement is constrained much better if you include the in-spiral and merger simultaneously. So clearly, to get optimal science out of the gravitational wave data that we are getting, it is necessary to use information from numerical simulations and fully nonlinear numerical simulations. So next, let's look at how we do these simulations at the moment and restrict ourselves to the compact binary system in doing so. So the basic, of course, is that we need to solve the equations of motion. For now, unlike Newtonian gravity, what we need to solve these equations are for the geometry, or rather the space-time metric that represents this geometry, and obey some field equations, which are written down here. Essentially, they comprise of a set of 10 second order in time and space differential equations that are coupled. And I don't need to tell you that to solve this large number of equations, coupled PDEs, is not easy for a variety of reasons. Some of these reasons we will see as we go along in this presentation. So the very first attempt to actually numerically solve these equations happened back in the day, 1960s, when Hahn and Lindquist tried to evolve two black hole system, but which they succeeded for a very in doing for a very short time before their numerical errors grew exponentially and pretty much killed the simulation. Right? And at that time, the expectation was that, hey, this problem is hard, but we can do it maybe in a few years of work. Well, it took up approximately 4 decades after this first attempt that the first successful simulations were performed by Franz Pretorius in 2005. And here we see the, I think, 1.5 orbit simulations at different resolutions that Franz performed. And on the right side, we see the emitted gravitational wave from each of these simulations. Soon thereafter, different groups writing independent numerical codes to solve Einstein's equations were able to also perform stable simulations, right? So in 2005, 2006, in a way, the field had become mature enough to finally do stable simulations 40 years after we started. So the basic methodology, of course, remains as one would naively think. The goal is, of course, to solve for the space-time metric as a function of time. And in order to do so, we start with splitting space-time into space and time. And by inducing this split, we also split Einstein's equations into 4 independent equations, 2 of which tell us how the spatial metric of each slice, or each time slice, evolves in time. So here, in this diagram, I'm showing a representative 3+1 split. So this is a three-dimensional spatial slice here, which is also a constant time coordinate slice. So all over the slice, the time coordinate is fixed to some value, say T1 here. Right? And so we have the intrinsic spatial metric here, which is Gij, and the extrinsic curvature of this slice, which is capital Kij. And two evolution equations tell us how these two evolve from one time slice to the next, while there are two more constraint equations that do not evolve time derivatives. Rather, they give us constraints on the geometry of each slice as we move from one starting slice to the next, and so on. So this is essentially how we evolve Einstein's equations given some initial state of the system at a initial value of time, right? And this is not a very new structure. For example, Maxwell's equations also give a somewhat similar structure. We get two evolution equations for the electromagnetic field and two constraint equations that don't help us evolve these fields, but do impose constraints on how the dynamics of this field from one time to the next can change. So what really makes it challenging? Why is it difficult? Why did it take 4 decades to achieve the first stable simulations, right? So there are many difficulties, and the first of which, of course, is that we have many length scales in the problem. Starting from the smallest length scale, which would be given by the size of the smaller black hole, which is maybe order of unity, let's say. Then we have the separation between the black holes, and then we have the wavelength of gravitational waves being emitted. Then our domain must encompass a few full wavelengths before we are able to measure the waves at the outer boundaries of our domain. And so the size of our simulation domain must be several wavelengths large. And also in terms of time scales, there's also the time scale of the waves propagating and the time scale of the gravitational wave flux, which is different from each other. So overall, we have 2 to 4 orders of magnitude in different length scales in the problem. Then we don't know what coordinates to use for a space-time we don't know yet, right? So when we do dynamical simulations, we don't know if we don't necessarily know if our choice of gauge and coordinates will actually work well for the simulation as the system evolves, or will we need to adjust it as a function of time and so on. Now, putting black holes on a grid is always a fun task, right? Because putting singularities on a numerical computation grid nothing bad will ever happen, right? Then the main issue that plagued the field for several decades was that Einstein constraint equations, the equations that I described here, which the left-hand side should identically remain zero throughout the evolution. What happened for decades was that even if we started with an initial data where this was satisfied, it did not continue to remain satisfied. And any smallest numerical errors that made the constraints non-zero actually grew exponentially. And it was not easy to understand why this was happening. And once people had understood, it took some time to understand how to control this from happening, right? So this was one of the last difficulties to be resolved before making these simulations possible. Then, of course, if we have systems with black holes and neutron stars, then we are bound to develop shocks. Maybe the star gets disrupted by the black hole, and we will end up with discontinuities, which are not always easy to handle. And of course, there are computational challenges. At any point, we're evolving between 20 to 50 variables. And because there are many length scales, there are many time scales. And if we take global time steps, that means we are pretty much taking the smallest allowed time step, or rather the largest allowed time step, which corresponds to the smallest length scale, right? So the smallest length scale dictates how quickly we integrate the whole system forward in time, right? Which is not very efficient. And there are many other things that contribute to inefficiencies of the evolutions in terms of the computational cost involved, right? So this is quite a challenging endeavor, and this is something that we still try to fight against, as we see in the sections to come. And of course, the accuracy required by our detectors is rather high. We need to have simulations that are very faithful, and they have errors much smaller than a single radian over tens of orbits, right? So we have simulations that are difficult to design, but the requirement is that they must remain stable and stable for a long time, and also come at a low computational cost. And that's what makes this entire deal challenging, right? But everything is not that bleak, at least for the vacuum problems where we have, say, only two black holes in a system. The solutions are at least guaranteed to be smooth. And in that case, we can address the questions of computation challenge and the accuracy requirement by using spectral methods. Which brings us to our particular numerical relativity code. This is called the spectral Einstein code, or SPEC. It was developed over several years by members of Caltech and Cornell, who then moved to different parts of the globe, and now have presence in many major universities across the planet, including ICTS. Um, and while the SPEC group was one of the last ones to perform the first stable simulations in full numerical relativity, we are definitely now the leading providers of waveforms to LIGO, and that is thanks to our use of spectral methods, which allows us to perform very accurate simulations at a fraction of the cost that other discretization schemes like finite difference codes uh, afford. Okay, and what is the beauty of these? What is the power of these spectral methods? Well, in the spectral discretization scheme, instead of representing every field that you're evolving at every grid point by its field value, we represent the fields by the sum of linear combination of some spatial basis functions, where the coefficients that go along with these basis functions themselves become functions of time. So every field is expanded in this form, and this separates out the time and the spatial dependence. And the gain here is that any spatial derivative operator that acts on this field acts only on the basis function, for which we know the derivatives exactly. So all our spatial derivatives, first order, second order spatial derivatives, they are computed almost exactly with no additional approximation, and they are also computed rather computationally efficiently. And this allows us to perform, to solve second order PDEs rather quickly, as compared to finite difference methods where a stencil must be created before a spatial derivative or two are taken at any point. And that is a more expensive procedure. So what about all the other goals that I just listed? Well, SPEC has the following technical solutions to some of these challenges. So to handle multiple length and time scales, we use adaptive meshes. These adaptive meshes are capable of becoming more or less dense depending on the length scales of the problem in question. So where the length scales are smaller, the meshes become significantly more dense, can be even 10 times more dense than in the regions where only the gravitational waves, say, are propagating, and there is not much dynamics happening beyond the propagation of these waves outward, in which case we can get away with a much less dense grid. Now, which coordinates to use? Well, we use coordinates called generalized harmonic coordinates, and they are quite nice. We'll not go into details of these, but we can always come back to this. Um, how do we put black holes on the grid? Well, we excise the singularities away, which means that we closely track the apparent horizons of all the black holes in our system, and we remove the interior of these apparent horizons from the grid. We don't place any grid points in the interiors, which means that we don't run into the risk of the singularity actually making contact with any of the grid points. Of course, this comes with the added complexity that we must track the black holes accurately all the time, right? Now, how do we handle the growth of Einstein constraints? Well, it was found collectively by different people that if you take the initial evolution equations, Einstein evolution equations, and you add terms proportional to the constraint equations on the right hand sides, what we find is that as the evolution proceeds, any violations of these constraints get damped away automatically on a time scale that we control. So in other words, even if numerical errors make for some of these constraints to become non-zero, the fact that we have modified the evolution system with these well-placed terms on the right-hand side means that these numerical errors decay back to zero as the evolution progresses. Okay, how do we handle shocks? Well, what we use are duplicate meshes, and this is not the best way of doing this, but um, we have one mesh where we use spectral methods for solving Einstein's equations, and we have a whole different mesh overlapping with this mesh, which uses finite difference discretization and solves matter equations and is able to handle any, say, density discontinuities that may come up as a simulation process progresses. Now, what about the last two needs? Well, we use spectral methods. They definitely help. And we use several optimizations in spec to make our simulations possible and faster and um, more accurate. Okay, so let's quickly browse through some of the key results that we have seen over the last few years, starting from the very first waveforms that were produced by spec in as early as 2007. Of course, this was a couple of years too late, but even then, this is the equal mass non-spinning simulation that we produced, and it was 15 orbits long. It was stable for that long, and it was in fact the longest simulation that was produced at that time, right? And in on this panel here, you can see how well the constraints are controlled. So here is the energy norm of all the constraints added together, and what we see is as a function of time, other than this initial phase here, we find that are at different resolutions. So each of these curves correspond to different numerical resolutions of our grid. The top one being the least dense grid, and the bottom one curve corresponding to the most dense grid. And we can see that the constraints are rather well controlled, and they are small all the way up to merger, where they seem to rise for all resolutions, but not too bad. And then they come back down again. And you can also see the power of spectral methods here, that by changing the resolution by the same factor, we actually get an exponential decay in these constraint violations. Okay. Because every time in spectral methods, every time you're changing the resolution, you're essentially adding a new basis function when you're representing your field. And that new basis function sort of is essentially brings about a logarithmic convergence of these. Okay, here in this figure is shown the phase accuracy and the amplitude accuracy, again at the same resolutions. And we can see that these accuracies also decay exponentially with increasing resolution, and they stay small throughout the time span of the simulation. Remember, this was the very first simulation, right? So a few years later, spec collaboration came up with the first public catalog of simulations that was made available for the entire community to use. And this was a big step at the time, because at that time, most of the simulations, in fact, all of the simulations were closed source, and all the numerical relativity codes were also closed source. So this marked a leap towards an open source culture in the field in 2013. Soon thereafter, we saw the first gravitational wave signal with LIGO detectors, and this was the 150914 signal. So we made this animation to reproduce what we think the source of the signal was like. So here are the two apparent horizons of the black holes. In the outer region, the color shows the gravitational waves going away. And in the inner region, the color shows time dilation, while the height of the surface here shows the 3 Ricci, rather the Ricci curvature of the spatial slice at any given instant in time. And because these black holes have spins that are not aligned with each other, we will see that the orbital plane actually precesses. So we'll see the orientation of this orbital plane change as the two objects come closer and closer to each other, as we're seeing now. And we slow down the simulation as we come closer to merger. We can see that in this highly dynamical regime, the spatial curvature is changing on very short time scales. And this is the moment when a common horizon is formed for the first time, which very quickly radiates away its anisotropies and settles down into a nice curved black hole. And here are the gravitational waves that have been emitted during this process, and far away from the source, we place a symmetry boundary on which we record these gravitational waves. And that's how we extract waveforms from these simulations. Now, only a year later, we made it yet another major addition to the catalog that we had made public in 2013 with 95 more simulations. Yet 2 years more later, we perform 1,000 simulations more, and we also release them to the public, bringing the total size of our catalog to about 1,400 simulations, right? And most of these simulations, as you can see, are a few tens of orbits long, right? So here, for example, are shown the waveforms coming from each of these simulations. They correspond to all sorts of configurations: black hole spins aligned with each other, not aligned with each other, small and large black hole spins, and even non-spinning simulations make their way here, although admittedly they're a minority here. Now, in the very next year, 2019, just a couple of years back, we performed yet another set of 2,000 simulations, and we also released them to the public. And so here is now a histogram of all of our simulations as a function of how long they are, how many cycles, gravitational wave cycles there are in these simulations. So we can see that there are definitely some very long simulations that we perform, but the bulk of our simulations seem to have around 50 cycles, right? And here are the set of their initial black hole parameters. So Q here is the ratio of the two black hole masses. Chi1 and Chi2 are the magnitude of the spin angular momentum on each of the two black holes. The label 1 for the more massive black hole, right? And so definitely over the years, we have come a long way as a whole, as a field, and the simulations have become much more controllable, much more easy to perform, if you would allow me to use the word. This, what the state of the field says, that the standard nearly equal mass simulations are now pretty much automatically performed by spec, and only the higher mass ratio simulations, or maybe simulations with very high black hole spins, are what require human intervention. So for example, stability was one of the first barriers that we had broken. And due to adaptive meshes that are self-refining, and better control systems that tell these meshes and the time stepper to when to perform mesh refinement, or when to maybe change the time steps and so on, we can perform simulations up to 35,000 M. And the longest that we have gone is, I think, 100,000 M long simulation for a mass ratio 7 system. This was no spins on the two black holes, but 180 orbits long. And so this is quite a feat in terms of the stability requirements that these simulations go along with. So how accurate are our simulations? Well, here's a histogram of our first 2,000 simulations and the errors on the x-axis. And we can see, well, there are some outliers. Most of our simulations are accurate up to 10 to the power 1 part in 1,000 in terms of mismatches between the highest resolution and the second highest resolution, which we take as a measurement of the accuracy of the highest resolution itself. How expensive are each of these simulations? Well, they still take around 10,000 to 20,000 CPU hours for about 20 orbit long simulations. And the cost, of course, depends strongly on the mass ratio and the spin on the smaller black hole, right? And so here are some example diagnostic plots from some of these simulations. So if we look here, this shows at different numerical resolutions how the number of grid points in the domain changes. And you can see these changes are because of our adaptive meshes that keep refining and unrefining as the simulation goes ahead. And at all resolutions, near merger, the meshes refine drastically, increasing the total number of grid points by a factor of around 3, right? But this again is temporary, and the simulation stabilizes back to its pre-merger level of grid sizes. Same thing happens here for the physical time that elapses into uh, each one of these simulations as a function of different resolutions. We can see the resolutions, the simulation speed is pretty much uniform. The speed is given by the first derivative of these curves, and they are pretty much uniform. The simulations slow down drastically near merger, but then they pick up pace again. Right? So this is typical of most of our simulations. Okay, so how have these simulations been already applied to gravitational astronomy? Right. Well, the most well-known, long studied use of these simulations and the waveforms coming from these simulations is in the calibration of approximate waveform models. So we have perturbative treatments of the two-body problem in under, say, post-Newtonian theory, for example. And that gives us a lot of information about the in-spiral, how the in-spiral part when the two black holes are far away and they are moving slower, much slower than speed of light, how they evolve, how their orbits evolve as a function of time is described well by post-Newtonian results. At some point, however, the black holes smoothly come close enough to each other, and the gravitational field becomes dynamical enough that these approximations, the approximations that underlie post-Newtonian theory, the slow motion and the weak field approximations, they become bad. They are no longer valid, and that happens when we are coming closer to merger, right? So what waveform models do is they take information from post-Newtonian theory, they take information from a set of numerical simulations of the merger part, and then they try to form a semi-analytic prescription of how to combine these two, how to interpolate between these two sources of information, right? These two rather mutually exclusive sources of information. I say mutually exclusive because NR cannot really go back into the spiral and evolve hundreds of orbits. It can do 20 orbits or so, but not hundreds or thousands of orbits. And same for post-Newtonian theory. It cannot describe the merger dynamics. So the two sources of information combine in waveform modeling. And it has been done for all the entire spectrum of binary mergers, from non-spinning binaries to aligned spinning binaries where the black holes have spins, but these spins are parallel to each other and also to the orbital angular momentum, which means there is no spin cross orbital angular momentum term. And so the plane of the orbit remains fixed. Then, of course, we have spin precessing systems where the two black hole spins are misaligned with each other. We have all sorts of precessional dynamics happening that is evidenced by this smooth fluctuation in the amplitude of this waveform, as you can see, as compared to this nice chirping feature that we get for the non-precessing orbits in the left two cases. And finally, we also have eccentric binaries, which essentially are binaries that are spiraling on elliptic orbits, right? And they have a distinct new time scale that has been introduced into the system. And that is visible in the phasing of these waveforms. So we have, in each of these panels, we are showing a model being compared to a numerical simulation. You can see the models are doing not terribly. They are always being improved. And so this is a major application of numerical simulations. Right, we can also do parameter estimation with these simulations directly. For example, the first few events, here is shown the measurement of the total mass of the system and the effective spin on the binary that caused that the gravitational wave signal that we observed, namely 59 and 14, 17 or 104. And in green is the measurement that we would have gotten using numerical simulations alone, which is actually very comparable to the other two contours here, the red and the black. And they are the measurements that we get from using approximate models. So the fact that they are quite consistent tells us that we can use numerical simulations directly actually to perform parameter estimation. And if we can also perform searches with these simulations if we wanted to. So this figure shows a dummy result from a search performed with only numerical simulations. And the figure here shows the total mass of the sources and again the effective spin of the sources on the x and y axis. And the color shows the fraction of the optimal SNR that this set of numerical waveforms will capture. Just to put this into context, I've marked the first few events that we had seen, and they lie bang in the middle of this entire space here. And we can see if we were using only NR waveforms to search for signals, we would have still seen these particular events loud and clear, right? And even for testing general relativity, of course, other than the fact that we need models that capture merger and ring down, there are additional ways in which NR results are applied. So for example, here is a test where we try to measure the mass of the final black hole, the spin of the final black hole, independently from the inspiral portion of the signal and from the merger portion of the signal. And we try to see if the two are consistent with each other, right? So this is a sort of a consistency test for GR. And the problem, of course, here is that when you're using the inspiral signal alone, you can only measure the properties of the pre-merger system, which is you can measure the masses of the two black holes that are about to merge and their properties. But you can't measure really the mass of the final black hole because you're only modeling the inspiral portion of the signal here. So what is done is that individual masses are measured, and then a mapping is used that maps these to the mass of the final black hole and the spin of the final black hole. And this mapping itself comes from the large NR catalogs that have been made available to the public. So without this mapping, this measurement would actually not have been possible, the inspiral only measurement, right? So yeah, so this was a quick tour of how NR is becoming more and more indispensable to gravitational wave astronomy, especially in today's times when most of the signals that we see come from heavy black holes. Most of the signals that we see contain only the last few tens of orbits before merger, right? Had LIGO seen only neutron star binaries, which have very long inspirals, then numerical relativity would have not had such an important role to play. But then, of course, we would have had also much lesser an opportunity to study really, truly strong field dynamics with these observations. So with excitement comes complexity. Okay, so final section of my talk in the last 5 minutes. Quickly, let me talk about where we are going from here. Right? So we go back to our scale, to a set of challenges in the field, and well, we realize that with spec, while we handle length scales, we really don't handle time scales properly. Our coordinate choices are robust, our handling of singularities are robust, our handling of constraints are robust, but spec is still terrible at resolving shocks, and the current method it uses is rather counterproductive, which is, remember I told you about this, we use two independent meshes. This is the spectral mesh and this is the finite difference mesh, and they're laid on top of each other. And then of course the computational challenges and accuracy requirements. While spec is good, it still needs a lot of improvement, especially to cater to the needs of LIGO as LIGO's accuracy is improving. for 3G detectors, and definitely for space-based instruments, where we will need a couple of orders of magnitude improvement in accuracy requirements uh, that are set by LIGO in today's date. Okay, so these four problems still remain. They are not very well solved. They have been solved enough, but not in a way that is future-proof, if I may use the word. So people went back to the drawing board and they realized that these are actually fundamental limitations of our numerical codes, and we need to change some paradigms before any improvements can be made. Small optimizations will not help. So the three paradigms that we had to change was the way we discretize the problem, the way we parallelize the solution, and the way we do time stepping, the way we handle time scales. And let's quickly talk about each of these, right? So discretization, well, since I'm short on time, let me just say that the scheme that we found after some review of the applied math literature to be the most robust is the discontinuous Galerkin scheme. And the benefits of this scheme are that whether we require low order accuracy or high order accuracy, the method remains local. It doesn't require uh, communication from its neighbors as a function of how accurate you want the simulation to be. Right. So this is, for example, not true for the finite difference methods, because the moment you increase the order of the accuracy required, you need to have a bigger and bigger derivative stencil. That means getting information from more and more of the neighbors at any given point, right? Then this method can handle discontinuity as well, which is unlike global spectral methods, which are unable to handle discontinuity actually. And it can do inhomogeneous grids, which most other standard methods are actually able to. But DG is the one method that is able to satisfy all of our requirements, especially for this heterogeneous system that we are trying to simulate, right? And what does DG do? So just like spectral methods, so imagine this is your entire domain, and each of these blocks are your subdomains. In each of these subdomains, we have some basis functions, and the solution is represented as a sum of the basis functions. So green is the true solution, purple are the representations of the solution. And right now, only two basis elements have gone into getting the purple lines, the constant term and the linear term, which is why these are lines. When we increase the order of these uh, basis functions here, as we include the quadratic and cubic order functions here, the representation of the true solution becomes more and more accurate. This part is like spectral methods, but what is not like spectral methods is that communication between elements need not be exactly continuous. We can allow for an approximate communication of flux information between any two given neighbors. And this is what really allows it to handle discontinuities, which, if you remember, is the only negative part of spectral methods. Okay, then we do local time stepping, and very quickly, what that means is that you can see that most of our simulation domain is empty, with the source being right in the middle, in the center somewhere. So local time stepping means that if you have the bigger black hole layer, smaller black hole layer, this is the empty wave zone. We take time steps according to the length scales. We take small time steps near the smaller black hole, larger near the bigger black hole, and definitely much larger time steps in this outer empty wave zone. And this gives us a significant improvement in the integration efficiency, right? And finally, the parallelization scheme, and I won't spend too much time on this. We used to use MPI parallelization, but because of how heterogeneous this problem is, all of our the slowest task was the one solving Einstein's equations near the small black hole. And this would make all the other MPI cores wait for it while it happily chugged along and completes the evaluation of the right-hand sides. A different method is to use a task-based parallelism where different cores don't necessarily solve the equations for different points in the domain. The entire global solution solving algorithm is broken down into very, very small steps. And each of these steps are queued on all the cores. So what that means is that once all the other cores are done solving integrating Einstein's equations for the empty part and so on, all of these cores will help the core solving Einstein's equations for the near the smaller black hole, where the smallest length scales are. Okay, so this means there's no more waiting. And as the final result, I'll show the scaling of this new code that we are writing, Spectre, which has these three distinctive new paradigms: DG methods, local time stepping, and task-based parallelism. And we see how on a standard problem set, the speed of Spectre scales as we go from using a few tens to 500,000 CPU cores to solve the same problem. The ideal case, of course, is a linear increase in speed. All of our current codes pretty much plateau after say about 100 cores have been already included. But the Spectre is future proof in the sense that you can actually throw a large number of CPUs at a complex enough problem and get the solution in a finite time still, which wouldn't be the case if the scaling plateaus like the old codes did. So this is actually a pretty positive and hope-giving figure that I would like to end this talk on. And to summarize, well, numerical simulations of binary black holes is key and essential to extracting scientific information from our ground-based observatories that are continuously recording gravitational wave signals. We have already seen 100 events, and we are not close to our design sensitivity yet. So I can only imagine what the future will bring us. And the chief way through which NR simulations help us are through improvements of waveform models that we use to extract these signals from data. Now, our first code spec was a flexible infrastructure, and it is still our flagship code that is producing some cutting edge science. Spectre is our new generation forward-looking computational astrophysics code, and it improves on three critical aspects. And these are the three things I hope you will take away from this entire talk, even if you forget most of it in some time. The three things to remember is the use of DG methods can really help with heterogeneous problems that have discontinuities. Use of local time stepping also helps significantly, and task-based parallelism is key to making your solvers scalable, especially to the future where we will have exascale computing, right? And so Spectre is not complete yet. Lots of bits and pieces are already in place. We are working on some of the final engineering solutions, and most importantly, Spectre is entirely open source. It is available on GitHub, and therefore we encourage all of you to look at it and possibly use it and tell us how the experience goes. So thank you all for listening, and I will take any questions if you guys have some.
Thanks, Prayush, for this brilliant overview of numerical simulation and the spec and spectra. So yeah, if you have any questions, please raise your hand. Yes, Professor Kandaswamy Subramaniam, please ask your question directly. Please unmute yourself and ask.
Hi, Prayush. An
Hi,
excellent,
Kandu.
very nice talk about, I mean, one of the few understandable talks on this subject which I've heard. I was wondering that, see, you're focused on, basically addressing LIGO kind of stuff. For example, one thing which you did not mention is the second last point which I've written about Einstein MHD equations implementation, right? And how much has that progressed? For example, can you follow the collapse of something to form a gamma ray burst or a jet and stuff like that, which would be really exciting for astro things other than just pure binaries, which is I understand that's the focus right now. But eventually these problems would be very interesting. So
Right.
I just thought I'd get your comments on what's happening there.
So core collapse supernova has been a rather elusive problem for the last few decades. We have been able to simulate MHD in full GR with spec, definitely, and that's been a possibility for years now. Yet core collapse supernova simulations, there seem to be always a need to seed the magnetic fields correctly before the collapse can happen. And we are hoping that with Spectre, once we get the power of using large scale supercomputers, maybe we can do numerically exhaustive simulations and surveys of the entire parameter space that seed those simulations to figure out what exactly is going on there. Maybe we can get some new physics out of these simulations, given the vast amount of computing that are available to us. But at this moment, with Spectre, the only application of GR MHD that we have done is the evolution of neutron stars and accreting neutron stars, and that we are able to do stably. And we recently put out an article on Archive talking about different ways of uh, handling the loss of high order. So let me rephrase that. We put the recent article that we put out was on a few different ways of handling discontinuities, which neutron stars eventually form. And that sort of tells you that Spectre is progressing in the right direction, and we are doing GRMHD in a sensible way. We still don't have very clever meshes that will allow us to do adaptive mesh refinement, and that's the technical part that is still missing. So we can only solve simpler problems right now. But as Spectre grows and matures more, I hope that co-collapse supernova will be one of the things that we finally extract something new about.
Yeah,
So
thanks.
I'm hopeful about
Yeah.
our prospects in the future.
Yeah, I mean, just to add, even forgetting MHD, there may be very interesting problems purely GR based of collapsing objects to form black holes and all that kind of stuff. So that's
Right.
been explored a lot. Or?
Yeah, that has been done with Spec.
Okay. Thank you, sir.
Yeah.
Thank you, Prayush. Very nice.
Mhm.
Thanks, Prayush. Since there are no other questions and we are already a little bit behind schedule, let me ask a very quick questions. In the third slide, you mentioned that in the flow chart, there was models and then you had the simulations, which goes to the Bayesian estimation.
Right.
I would like to ask in the models, basically by the models, you mean the spin, etc., and not the models like GR or beyond GR, right?
Right. These are various ways of solving GR. So
Okay.
post-Newtonian based models, effective one body mapping based models, or just purely phenomenological models that take GR and take your two body problem with or without matter and solve Einstein's equations approximately to give you the final waveforms. So they are all GR models, only different ways of approximately solving Einstein's equations.
Okay, I understand. So these codes do not deal with models beyond GR, or if
No.
okay, don't test these models. Okay, thank you very much. Okay, so let's thank Prayush once again.